and welcome to our fourth video in AP Chem. So we have physical versus chemical changes. Please also make sure that you're referring to pages 9 to 11 in our TRO 3rd edition. So we're going to talk about definitions of physical and chemical properties and changes, and discuss examples of each. So physical, pretty much these are going to be observed with our senses, and we're not going to be able to, we're not going to destroy the composition of any object. For chemical property or chemical change, we're going to see how the how the substance reacts with something else, and we essentially change what happens chemically. We need something called a chemical equation to help us figure out what's actually happening with these chemical changes as well. And we'll discuss chemical equations later on. We'll be doing a lot of them. So physical properties. Pretty much this whole list, we've got color, odor, the smell, the shape of an object, the mass, the length, its taste. We typically don't taste anything here in chemistry. Its luster, how shiny it is, how malleable it is, or how it can be hammered into shape, ductile, how it can be stretched, the boiling point, so the temperature at which it goes from a liquid to a gas, and then its melting point is the temperature at which it goes from a solid to a liquid, and also its density. So we have something called intensive versus extensive properties. I'm going to throw this at you right now. We'll see a little bit more about it later on, but pretty much an intensive property, and I'll write it down over here. Whoopsies, yeah. My wonderful little stylus here, guys. So an intensive property is independent of how much of an object, or how much of the substance that you have. An extensive property is dependent on how much you have of the object. Okay? So an intensive property, again, independent of how much of the substance you have. So if you have, and let's kind of think of that, some modeling clay, all right, or some Play-Doh. If you have a little piece of Play-Doh or a large amount, its color will always be the same. Its odor will be the same. Shape is kind of a weird little way to do it. It might taste the same, so if any of you guys have tried Play-Doh, I never have, but people say it has a distinct taste to it, sure, whatever. Its luster, its malleability, its ductility, and the biggest things are boiling point, melting point, and density. Those are all intensive properties, so it doesn't matter how much of the object you have. Those are all going to be the same if you have a little teeny tiny piece or a whole big tub of the same type of Play-Doh. An extensive property is going to be based upon how much of that object you have. So in this case, mass, length, and also we'll add in here volume are all depending on how much you have of that object. Okay? So that's the definition between intensive versus extensive. So here we've got its how shiny it is, or its luster. This represents a sheet of copper that it can be hammered into shape, so that's going to be how malleable it is, and copper being drawn into wire, and that's how ductile it is. So chemical properties are all based upon its composition, so what it's made of. In this case, we have a penny. Its outer material is made of copper, and that's one of our elements on the periodic table. But if you actually take a look right here, this penny is made in 2001, pretty much 1983 and beyond. We actually, let's say 1982 and before. So anything older than 1982. Pennies were made of pure copper, so if you snapped it in half, the whole thing would be made of copper. Because copper ends up being pretty expensive, in 1982, the U.S. Mint decided to go ahead and make the core of a penny made out of zinc, which is a much less expensive material, and then just coat it in copper instead. So that's actually just a little fun fact about pennies themselves. So if you take a look here, if you break that penny, or if you break the penny essentially, you'll see that's like a silver material. That's all made of zinc inside. And we need a scanning electron microscope to help us determine what that composition actually is. And this is showing you pretty much just the atoms themselves of, in this case, copper. Alright, so physical changes is any change in state of matter. So remember in the last video we talked about solids, liquids, and gases. So from solid to liquid, we have melting, liquid to a gas, we have evaporation, vaporization, or boiling, and then we have the reverse processes as well. So gas to liquid, you have condensation, and liquid to a solid, we have freezing. So those are all dealing with changes in states of matter. So again, here we've got melting, in this case, of an ice cube, going from a solid to a liquid, and freezing. It's going to occur at the same temperature, so we say that those are all at equilibrium. We have boiling and evaporating, a liquid to a gas, and condensation's gas to a liquid. If you note here, take a look at all of these chemical equations, essentially, and that's when you have the formulas on the left and right-hand side divided by an arrow. So if you notice, on each side of the arrow you have water. It's just their states of matter that have changed. So that's how you know if something's going to be a physical change instead of a chemical change. Don't forget to make sure that you know what it is between a solid and gas, and then a gas to a solid. Dissolving. So anytime we're mixing something in water, we call that an aqueous solution. If you think about in Spanish, water means agua, or water is agua. So aqueous means mixed in with water. Now this whole dissolving part, it's kind of weird. So sometimes, like, some scientists think it's physical changes, some think it's chemical changes. For the most part, we've seen that dissolving is a physical change, so most scientists agree it's a physical change, but there is a lot of stuff that's happening that's chemically going on. But it just depends on the substance itself. So if we have sugar dissolving in water, that's just mixed in. But we have something like table salt. Well, table salt will actually break apart into sodium and into chloride. So we'll discuss that later on. But some people consider that the chemical change. So essentially we're mixing things with other substances. Chemical changes are a change in that composition. So we have to look at our chemical equations to help us figure that out. On the left, and with these, I always want you to find the arrow first, and then look at the left hand versus the right hand side. So on the left-hand side, we have CH4, which is something called methane, and we have O2, or oxygen. On the right-hand side, we have CO2 and H2O. So essentially, we're showing that methane and oxygen, when we put them together, they produce, and that's what the arrow represents, it means to produce, carbon dioxide and water. That's going to be a chemical change. Big word of wisdom, if you see the words reacts with, you know it's going to be a chemical change. So for example here, methane reacts with oxygen to form carbon dioxide and water. Here is a representation using those particles that I had shown you before. So pretty much these black spheres represent carbon, the white ones represent hydrogen, and the red ones represent oxygen. That's pretty universal as well, so you want to make sure that you kind of create yourself a key for that and know what that means. So quick thing with chemical equations, we have methane right here. There's no number in front. So the numbers in front, like we have a 2 there and a 2 right over here, we call them coefficients. So just like in math class when you have a coefficient, it's a number in front of a variable, kind of the same thing here. So even though there's no numbers in front of the CH4 and the CO2, there's an invisible 1 hanging out in front of each one of them. So essentially we have 1 methane reacting with 2 oxygens to produce 1 carbon dioxide and 2 waters. All right, so make sure you take a look at those coefficients as well. Anytime you see fizzing or bubbling, generally that's going to be a chemical change. Now, of course, I'm kind of talking about like water here, or not with water. So if you take liquid water and boil it into a gaseous state, yes, that's forming bubbles, but that's all still going to be water vapor trapped in there. You're not creating anything new. Instead, here we have Alka-Seltzer tablets in water. So the fizzing is going to be produced as a result of carbon dioxide being produced. If anything is rotting or decomposing, like these lovely little strawberries right over here, that is a chemical change. And so make sure that you know the difference between the two. So chemical change. These are the 3 key words I want you to remember, or 3 key terms. Reacts with, combust, or decomposes. Those are all chemical changes. If it's a physical change, you change the state of matter, or it can dissolve. Let me know if you guys have any questions.